Today's topic is called P-series. That's right, P-series. The P stands for power. Every P-series should look something like this. And what we notice is that each term is a fraction, where the divisor, the denominator, is a power of the term index. So we have all these little powers down here, and each one has a different base. The base is not consistent. Instead, if this says the sum from n equals 1 to infinity, if this is the first, second, third, fourth, and fifth term, and so forth, each one of these powers uses that index as its base, and then it's elevated to some consistent power p. And that's why these are called P-series. Today you're going to learn to recognize P-series, and you're going to learn to distinguish between the ones that converge and the ones that don't. So first we'll look at a bunch of P-series that do not converge, and the reason they don't converge is because the terms, I should say, don't get small enough fast enough. Okay, here's an example of a P equals 1/3 series right here. It's typically going to be written like where the divisors are the cube roots of the term indices, cube root of 2, cube root of 3, cube root of 4, etc. But of course we know the cube root is really the 1/3 power. So in the second term I have 2 to the 1/3 power. In the third term I have 3 to the 1/3 power. And these are my divisors. This is a P equals 1/3 series. And you will soon know that that series diverges. Something a little more familiar might be square roots. So I have a series where each term is 1 over the square root of the term index. Here the term index is 4, and I have 1 over square root 4. But remember, something like the square root of 5 can also be written as 5 to the half power. So when you think of it this way, you can see it truly is a P-series where P equals a half. And again, this series diverges. Okay, P is supposed to be a positive number. It can be any real number. There's a threshold where you can tell that a series is going to converge or diverge just based upon comparison to the threshold, and we're about to get to that threshold. Okay, in this series, it's famous, it's called the Harmonic Series. It appears that there are no powers on the divisors. It appears we're just dividing by the term indices. Index is 3 divided by 3, index is 4 divided by 4, but you can always put the default power of 1 on there. And then this does become a P-series with P equals 1. And this diverges. So to review, so far we've seen a P equals 1/3, P equals a half, and P equals 1 series. And these have all diverged. But notice that each one of these values for P came somewhere in this range. 0 was less than P was less than or equal to 1. The rest of our examples are going to have P values that are strictly bigger than 1. And let's take a look at some of those now. Okay, this complicated looking series has values of each term index in the divisor, both cubed and square rooted. Here the term index is 5. But before I divide by it, I cube it and square root it. Well, you can twist that around to look something like 5 to the 3 over 2 power. It's a rational exponent. And you can do that all the way through. Each one of these divisors is a term index raised to the 3 over 2 power. Of course, 3 over 2 is 1.5, and this is our first example of a convergent P-series. This one looks a lot more attractive. It's just got the term indices squared. Here's the term index 5. I'm squaring it and then dividing by it. Likewise, when the term index is 4, square it to get 16 and then divide by it. Now, more often than not, this series is going to be written like this, and you're going to have to recognize 4, 9, 16, and 25 as perfect squares. Squares of the term indices. So this is a P equals 2 series, and it converges. One more example. If I'm dividing by the cubes of the term indices, like you see here, This is a p equals 3 series, and it converges. More often than not, it will be written like this, so it's a good thing to know at least a few of your whole number cubed values. So for example, this is 5 to the third power. This is 6 to the third power, and when you recognize this, you can quickly identify this as a p equals 3 series. Well, I think you probably saw where the threshold was. What you're looking for, if you want your p series to converge, it needs to look like this. P needs to be strictly bigger than 1. And then your p series will converge. And we already saw what happens if you're on the other side of this threshold. So that if 0 is less than p is less than or equal to 1, your series will diverge. Okay, we have some examples. Does this series S converge or diverge? What does the ratio test tell us? Well, it's too bad they asked that question, because I don't want you to get in the habit of applying the ratio test to this. Nevertheless, we're going to do it because we've been asked. So let's see. First of all, the ratio test. What do we need? We need the nth term. The nth term appears to be 1 over the 4th root of n. We're also going to need the n plus first term, the one right after it. And if you don't know the ratio test, I think I already have a video up on the channel where you can go learn about it. But the next term would be the 4th root of n plus 1. And in the ratio test, we're just going to divide those and take the limit as n goes to infinity. So we take the limit as n goes to infinity of the n plus first term over the nth term, and technically you should have absolute values around this, but everything here is positive, so it's not going to make a difference. So this is the limit as n goes to infinity of this divided by that. Well, when you divide a fraction by a fraction, the dividing fraction ends up looking inverted. So I'm going to skip a step here and just tell you that what you would see next is the 4th root of n divided by the 4th root of n plus 1. And now, of course, two radicals of the same index divided can be written as a single radical, like this, 4th root of n over n plus 1. And as long as we're talking about positive values of n, the 4th root is a continuous function, and so we can let the limit go inside the 4th root. That would look like this. 4th root of the limit as n goes to infinity of n over n plus 1. Well, a very, very large number, let's say like 1 million here, and 1,000,001 here are going to divide to something like 0.9999. You can always run L'Hopital's rule on this, take derivatives here and here, because you have a form of infinity over infinity, and the derivative of n is 1, and the derivative of n plus 1 is 1, so you would end up taking the limit of a constant 1, and in the end you'd get the 4th root of 1, which is 1. Now, it's always disappointing when you run a ratio test and it comes out to 1, because you cannot reach a conclusion about convergence or divergence. So it would have been better to avoid this test altogether and just go back and say, well, what kind of a p-series are we looking at here? 4th root is the same thing as a 1/4 power. So this is 2 to the 1/4, 3 to the 1/4, 4 to the 1/4, 5 raised to the 1/4 power. Yes, this is a p-series, and p equals 1/4. So S is a p-series with p equals 1/4, or 0.25. Well, since we have 0 less than p as less than or equal to 1, S diverges. And that's why you want to know something about p-series. Know how to recognize them, know what the threshold value is, 1, and know that a lot of series they're going to throw at you are just p-series in disguise. And I hope we also learned from this example that the ratio test is not going to help. Okay, we've got some more examples here. Show that the harmonic series diverges by comparison to an improper integral. Okay, now remember the harmonic series, I had that in my table, looked like this. It was a p equals 1 series. It certainly diverges. And in most situations, if you identify it as a p-series with p equals 1 and mention that that p-value is lower than the threshold, you can go ahead and say, oh, this just diverges. Or in a lot of cases, you can say, oh, it diverges because it's the famous harmonic series. But here they're asking us to do something more. And really, this is why the threshold is the threshold for p-series. So let's take a look at this. You write down the harmonic series like this. And you go ahead and leave little spaces next to each one of these fractions. And then go to each one of these little spaces and multiply by 1. Certainly that's not going to change anything, right? And why am I doing this? Well, we're going to learn to recognize each one of these little products as the area of a Riemann rectangle. So, we'll take a function called f of x equals 1 over x. And I think we all know what the graph of that looks like. In the first quadrant, it looks something like this. And we'll go to x equals 1, and x equals 2, and x equals 3. And after you've done 2 or 3 or 4 of these, you'll understand the pattern. But anyway, in the space between 1 and 2, I'm going to draw a Riemann rectangle. And it's going to be a left Riemann rectangle, or in this case, because I have a decreasing function, it is an upper Riemann rectangle. Well, how wide is it? Well, that's easy. It's 1. Well, how tall is it? Well, you have to plug 1, the sample point, into this function. So the height of this thing, let's call it h1, is what you get when you plug 1 into this function right here, which is 1 over 1, which is just 1. So what's the area? The area is 1 times 1. That's what that is right there. Let's draw another Riemann rectangle in the interval between 2 and 3. Let's make it a left Riemann rectangle. It's also an upper Riemann rectangle. Okay, how wide is it? That's easy. How tall is it? Well, that's determined by plugging this 2 into f of x. So the height of this second rectangle, let's call it h2, is f of 2. And that's just plugging 2 into that. Well, that's 1/2. That's the height of this rectangle. So the width is 1, and the height is 1/2. And the area is the product of 1/2 times 1. That's what that is. Do we need to see another one of these? I think you get the idea. So each one of these is the area of a Riemann rectangle. And each one of these Riemann rectangles is an upper Riemann rectangle, and it calculates more area than you'd actually find under this curve in this region. So what we're going to do is just sort of use that visual or geometric argument to say that all this stuff here is a whole bunch of Riemann rectangle areas, and they're all upper Riemann rectangles. So this thing has to add up to more than the definite integral from 1 to infinity of 1 over x. And we're going to show that this is infinite, and that'll prove that this diverges. Okay, how do you show that this is infinite? Well, because it's an improper integral, you're supposed to use limit notation here. Take the limit as b goes to infinity of the definite integral from 1 to b of 1 over x. And then if this limit exists, then we can talk about this as the area trapped under this curve. So how do you get this? Well, you need an antiderivative for 1 over x. For positive values of x, that's just natural log of x. I won't worry about the absolute value. So the antiderivative here is natural log, and by the fundamental theorem, I'm going to plug the b and the 1 into the natural log. And so that would look like natural log b minus natural log 1. The upper and lower integration limits plugged into the antiderivative of 1 over x. Then you just have to take the limit as b goes to infinity. Like that. Well, it should be pretty clear. This is the natural log of infinity minus the natural log of 1, which is infinity minus 0, which is infinite. Well, by the transitive property of equalities and inequalities, we have, what do we have? We have the harmonic series equal to this, but this is greater than infinity. So s is greater than infinity. So we conclude by saying the harmonic series, which we're labeling s here, diverges. And why? Since s is greater than infinity. There's the argument. And hopefully we won't have to do that again. Third example. Here's a Taylor polynomial. It's a Taylor polynomial for a function f expanded around x equals 3. Okay, one of the things they may ask you to do on a national calculus exam, I don't think I'm supposed to mention the name of it due to trademarks and so forth, but I know a lot of students are going to be confronted with this soon. Here's a question I wrote that's similar to questions I've seen on that exam in the past. They're going to want you to be able to expand sigma notation for a Taylor polynomial. This subscript 2 means second degree. They explain that. And then they're going to want you, after expanding it, to be able to evaluate it at 2.8. And in most years, you would have to be able to do this without a calculator. Let's see if we're up to the challenge. Okay, plugging in a 1, we get x minus 3 to the first, and we get 1 cubed. So that's x minus 3 to the first over 1 cubed. No, I didn't really need these here, but I'm just being consistent with the pattern. The next thing to do is plug in n equals 2. You're going to have 2 cubed on the bottom and x minus 3 squared on the top. And you may consider this done at this point. It's second degree after all, right? So my answer to this would be, first of all, the second degree or quadratic Taylor polynomial expanded around x equals 3 would just look something like this. X minus 3 plus 1/8 x minus 3 squared. All right, the next thing they want you to do is evaluate that at 2.8 to approximate f of 2.8. So be careful. Don't write something like this. Don't write f of 2.8 equals and then just plug 2.8 into that. You want to be sure to use this approximation symbol if you're going to introduce that right now. So it's approximately equal to what I'd get when I plug 2.8 into this little quadratic Taylor polynomial. And what does that look like? Well, 2.8 minus 3 plus 1/8 of 2.8 minus 3 squared. Well, this is pretty clearly negative 0.2. This is negative 0.2, but if I square it, of course, that becomes positive 0.04. And I think I'm going to convert all these into fractions now, or in the next step. So this is positive 0.04. Now, in terms of fractions, this is negative 2/10. And 0.04, of course, is 4 over 100. That's also 1 over 25. So we're getting a little arithmetic lesson here. When I multiply 8 times 25, that's 200. So I have negative 2/10 plus positive 1 over 200. And I can get both of these in terms of 200 just by multiplying these by 20. So this is 20 times 20 is negative 40 over 10 plus 1 over 200 makes negative, excuse me, I'm multiplying by 20. So this is also 200. That was the point. Anyway, this is going to make negative 39 200ths. All right, and by this chain of equalities, I think we've done a good enough job to show that this is the approximation for f of 2.8. All right, next question related to this. Find f double prime of 3. Well, this is a sneaky question. So remember that when you make a Taylor polynomial for a function f expanded at 3, the terms look something like this. P of x is supposed to be f of 3 plus f prime of 3 times x minus 3 plus f double prime of 3 times x minus 3 squared. And remember, this is where you have to start dividing by factorials and so forth. Well, I've gone far enough with this, haven't I? Because we had, on the previous page, written out the quadratic version of this, where it had no constant term, but it had x minus 3 as a linear term. And then for the quadratic term, it had 1/8 x minus 3 squared. Well, I think it's pretty clear from this that this coefficient can be used to help us figure out what f double prime of 3 is. Just set those equal. So I have f double prime of 3 over 2 factorial equals 1/8. Multiply both sides by 2 factorial, and f double prime of 3 is equal to 1/8 times 2 factorial, which just makes 1/4. And that is the value of f double prime of 3. What's the value of f prime of 3? They didn't ask us that, but if they had, we'd go back here, and we just compare to this coefficient. F prime of 3 must be 1. So we must have an increasing function with upward concavity, as these are both positives. And this function must have a 0 at x equals 3, because this term is 0. All right. Write at least 5 terms of p prime of x. Okay, to get p prime of x, you're going to want to expand what p of x was in the first place. So remember, p of x in sigma notation is the sum from n equals 1 to infinity of x minus 3 to the n power over n cubed. So let's write out some terms of p of x. P of x is, when I plug in a 1, x minus 3. When I plug in a 2, I get x minus 3 squared over 2 cubed. Yeah, we've already seen this, haven't we? But let's write down some more terms. Plug in a 3, x minus 3 cubed over 3 cubed. Plug in 4, x minus 3 to the 4th over 4 cubed. And since I'm supposed to have 5 terms of p prime, I'm going to go ahead and write out the 5th term of p. It's x minus 3 to the 5th power over 5 cubed. Now, what does p prime look like? Well, the derivative of this is 1. The derivative of this is 2 times this polynomial to the 1st power. Chain rule is not necessary on this, is it? To the 1st power. The 3rd term would have a derivative that would look like 3 times x minus 3 squared over 3 cubed. The 4th term would have 4 times x minus 3 to the 3rd power over 4 cubed. And as you can see, this problem is designed to have a lot of cancellation in it. And what's going to cancel? Well, each one of these binomials is multiplied by the index here and the 3rd power of the index down here in the divisor. So you can cancel. So here's the best way to write 5 terms of p prime of x. 5 terms of p prime of x. Here we go. We'll keep this 1. We'll cancel one of these 2's and write x minus 3 over 2 squared, which is 4. Okay, we'll cancel one of these 3's, and now we have 3 squared on the bottom, which is 9. So this is x minus 3 squared over 9. And then I'm going to have, after canceling some 4's, I'm going to have 4 squared. That looks like this. And then the next term is going to be, after canceling 5's, I'll have 25 here, and I'll have x minus 3 to the 4th power. And that is what p prime of x looks like. Got a little sloppy there. Sorry about that. Now finally, how do we know p prime of 4 converges? We haven't said anything about p-series in a while. Well, this is a p-series question. Plug in 4, and you'll see that each one of these little differences up here in the numerator, it makes 1. 4 minus 3 is 1, 4 minus 3 is 1, and so forth. And so if you're extra cautious, you might write something out like this. P prime of 4, okay, don't put x here because you're evaluating, is 1 plus 1 over 4 plus 1 squared over 9 plus, again, 4 minus 3 is 1, so I have 1 cubed over 16. But of course, you don't really need 1 squared or 1 cubed or 1 to the 4th for that matter. These are all just a bunch of 1's, aren't they? So a nicer way to write p prime of 4 would be 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25. What comes next? Of course, it's 1 over 36 because these are just the reciprocals of the squares. And this is a p-series with p equals 2. So you would write, finally, p prime of 4 converges since it is a p-series. And the p is bigger than the threshold. It's bigger than 1. And you really need to say that in order to have a valid argument here. Well, that's it for P-Series for today. Hope you enjoyed this. My name's Eric. Have a good day.